In general, proving that a series is convergent can be quite difficult. So far I have found very few series whose value I could compute from the definition. There is a family of series that are a bit easier to work with, positive series. It may still be hard to find the exact value of these infinite sums, but at least we have a simpler way to determine whether they are convergent or divergent, whether they add up to a number or not. In this video, I will define what they are and I will explain why we like them. First, some definitions. A positive series is simply a series where all the terms I am adding are positive. That's it. I can also define negative series in a similar manner, and I can also define, for example, non-negative series, where all the terms I am adding are positive or zero, and so on. Why are positive series easier? A series is defined as the limit of a sequence, the sequence of partial sums. An arbitrary series may be convergent or divergent. If it is divergent, it may be divergent for all the reasons that a limit may not exist. Perhaps it is divergent to infinity, or divergent to minus infinity, or divergent oscillating, which just means divergent in a different way. That is for an arbitrary series. But what about a positive series? For a positive series, there are only two options. It can only be convergent or divergent to infinity. It cannot be divergent to minus infinity because I would need negative terms for that. And it cannot be divergent oscillating because I would need both positive and negative terms for that. I think it's intuitive that these are the only two options for a positive series. But if we want to write a rigorous proof, we can do that as well, and it is quite quick. Here is the proof. As you know, the value of a series is defined as the limit of the sequence of partial sums. What happens if I assume the series is positive? In that case, the sequence of partial sums is increasing because I just keep adding positive terms. Or in other words, because the difference between two consecutive partial sums is one of the terms I am adding, which is positive by assumption. And then we can use the monotone convergence theorem. An increasing sequence is either bounded or unbounded. If it is bounded, then it is convergent. That is the monotone convergence theorem. And if it is unbounded, then it is divergent to infinity. That's it. That completes the proof. As you see, the proof consists of putting into formal language the intuitive argument I gave earlier. This leads us to a new piece of notation that is very convenient for positive series, because it is simple. But beware, we use this for positive series only. We're going to write that a positive series is either infinity or less than infinity. We will write infinity when it is divergent. That is the only way for positive series to diverge. And we will write that the series is less than infinity to mean it is convergent. Again, we only do this for positive series. An arbitrary series that is not infinity may still be divergent in a different way. But a positive series that is not infinity must be convergent, must add up to a number. One more note. So far I have been talking about positive series only, but everything I have said also works for non-negative series. If all the terms I am adding are either positive or zero, I can still draw the same conclusions. Even further, everything also works for eventually non-negative series. If the first 5 terms are negative, and after that they are all positive or zero, we still draw the same conclusions. Okay, so positive series simplify things. How is this helpful? To prove that a positive series is convergent, to prove that it represents a number, I only need to show that it is not infinity. That's all. Instead of proving that the limit exists, I only need to prove a limit is not infinity. That is less work. There are 3 theorems that utilize this fact: the integral test, the basic comparison test, and the limit comparison test. In the next few videos, I will introduce these results and illustrate how to use them with examples. They all have something in common. They can only be used on positive series, and they all rely on the fact that a positive series can only be convergent or infinity.